Hello everyone, good morning. Welcome to the NICKEFFECT and FreeMe webinar about materials modeling for sustainable materials development. Today we will showcase how advanced materials modeling are accelerating the creation of sustainable materials and driving the transition to a greener economy. Today with you, representing the NICKEFFECT project, we have Guillaume Bruni from Mechanics. And representing the FreeMe project, we have Constantinos from Excelsis and Albert Redon from Edener. Without further ado, I think we can start the presentation, the juice of this content. Maybe we can start with the presentation from NICKEFFECT. Guillaume, when you're ready,
Yeah,
you can share
I
your
will
screen.
share my screen. Can you see the screen now?
Yes, perfectly. What is yours?
Okay. Well, thank you for the introduction and for organizing the event. So as you said, I'm Guillaume Brunin from Magenics, a small company in Belgium, and I will present the work that we have done with UAB, the University of Barcelona, in the framework of the NICKEFFECT project. So it will be about atomic modeling using DFT, so density functional theory, and machine learned interatomic potentials on one hand, and then also process optimization through active learning. So first, just a few words about the NICKEFFECT project to have an idea of why we do what we do. So you may know that platinum group metals, so PGMs for short, are used in a lot of applications because they are very good catalysts. So just take platinum, for instance. Platinum is used in many, many applications. The thing is that in Europe, we have to import those metals. So we have to import platinum. And the NICKEFFECT project aims at replacing these PGMs by nickel in ferromagnetic coatings in three different applications. Two of them are related to hydrogen, so it's water electrolysis and fuel cells. And then there's also digital storage devices, so random access memory devices. And the role of Magenics in NICKEFFECT is to help the experimentalist partners to accelerate the design of new materials using first ab initio calculations. So this is DFT, density functional theory calculations, and also machine learning. And so now I will go through two examples of small projects that we did that we helped within the NICKEFFECT project. So the first is about using machine learning to optimize an experimental process. And so there we had discussions with UAB, the University of Barcelona, and they were depositing nickel tungsten films using different electrode deposition parameters. So they were using two different baths. They were trying different temperatures, different current densities, and different deposition times. And so they had different nickel tungsten films, and we wanted to see if we could help improve the performances of the films by tuning these parameters. And so they were doing these experiments. They were depositing these films and measuring the electrocatalytic activity. And so we were getting these kind of curves, the LSV linear swift voltammetry curves, so the current density versus the potential for different cycles. So there were 200 cycles and we took 6 of them. And so this is really the raw output, so these curves. And then the first step was to write a small Python script to automate the extraction of some quantities from these curves. And so the first quantity that we extracted was the over potential at minus 10 milliamp per centimeter square. And then we also got the Tafel slopes at minus 1 milliamp per centimeter square. And so we got that for 6 cycles, LSV cycles. And then the question is, how do we compare two films? How do we know which one performs the best? Because we have the overpotential and the Tafel slope for 6 cycles. That means we have 12 outputs. So we may have one Tafel slope that is better for a film, and then the potential is worse for this film. So how do we actually rank the films, and how do we quantify the performances with a single number that's easier to interpret? So for this, we defined two quantities. First, the evolution of on one hand the potential and on the other hand the Tafel slope. So the evolution is between -1 and 1. -1 meaning that the evolution was very bad, the sample degraded, and +1 meaning that the evolution is positive for the sample. And then we also define the global score for the film. That includes the potential at the first and last cycle, the Tafel slope at the first and last cycle, and also their evolution. And so we want basically a positive evolution. We want the sample to evolve positively. And we also want the Tafel slope and the potential to be as low as possible in absolute value, so as close to zero as possible. And so we define this score so that the larger the score, the better the film in the end. And so using this score, we can actually rank the different films that they were depositing. And so what we did exactly is we started from the experiments that UAB had done. So they had grown 24 samples for which they had the LSV curves. So it's not a lot, but still it can be used to train a machine learning model. In this case, it was a bugging of random forest models because random forest works quite well when you don't have a lot of data. And so you can see we have errors of 22% on the Tafel slope, of 30% on the score. These errors are quite large, but I mean, we have 24 samples, so that's the best that we can do at that stage. Still, we can use the machine learning model to provide suggestions of the next electron deposition parameters to try. So these suggestions will be, for instance, the parameters where the score is the largest according to the model. So at what temperature, at what current density, and in what bath will the score will be the largest for the deposited film. Another type of suggestion is also based on the model's uncertainties. So with the prediction of the model, you also have a measure of how the model is sure of itself, kind of an error bar on the prediction of the model. And if you provide suggestions where this error bar is the largest, and then these are done in the lab, you really reduce the uncertainty of the model in the most optimal way. So that in that way you optimize the model before optimizing the output. And then there's also a trade-off between the two. It's called using the acquisition function, where you optimize both the output and the uncertainties at the same time. Once we have provided the suggestions to UAB, they can do them in the lab, so they can do the new experiments, and that adds new experimental results. If we are happy with the samples that have been grown, then we can stop. Otherwise, we can use this additional data to train a new machine learning model. Then using this new machine learning model, we can provide new suggestions that should be better than the ones before, and so on and so on. And so this is called the active learning methodology. And in this small project, we started with 24 samples, 24 films that had been deposited. Then we suggested 16 of them, 16 new parameters. So we had 40 after this step, after this first round of active learning. And then we suggested 17 more. So we had, in the end, 57 samples that had been deposited by UAB. And among these 17 samples, we had one that was actually performing the best among all of the others. So you can see here on the left, each color represents a film, and we want to be as much to the right as possible. And you see that the yellowish gold one here, the ML optimized one, is indeed the best one. You can see here as well on the right, it's the same but in different scale, that we want to be as high as possible in potential, and indeed the ML optimized is performing the best among the other ones. And so all this has been written and published in a paper here that you can go check out if you want all the details. We can also discuss during the question time later. And another thing that I wanted to add is that machine learning models, using a machine learning model to model a process like this, can also help by bringing insights into what happens. And so this is done usually through visualization. For instance, here you can see how the Tafel slope, how the potential, and how the global score evolves with the temperature and the current density. And so you can see here that there's really a sweet spot for the score in terms of temperature and current density, where that you should aim for if you want the score that is high. And this really can help bringing insights and understanding using the machine learning model. Okay, so that was the first example, the first small project. Now, the second mission that we pursued within NICKEFFECT was about using density functional theories, actual simulation, and machine learned interatomic potentials to better understand ionic motions in crystals. And so it was again work that was done with the University of Barcelona. And in this case, they were depositing these nickel cobalt microdots arrays, and they were oxidizing the dots by first annealing at a given temperature for some time. And so the dots were actually getting oxygen and going from a magnetic state to a paramagnetic state. And after that, they were applying a voltage to the dots to remove the oxygen atoms and recover the nickel cobalt alloys, and then also recover the magnetic state. And the thing that they wanted to understand was why the annealing conditions, so the temperature and the voltage, were different depending on the nickel cobalt ratio, the content ratio in the dots. So if there were more nickel in the dots, then they needed a larger temperature to anneal and go to the paramagnetic state. And they also needed a larger voltage to remove the oxygen atoms and recover the magnetic state. And so to better understand that, we decided to use molecular dynamics to understand how the oxygen ion migration happens in these systems. And so we consider the cobalt oxide and the nickel oxide crystals, and we know that in these systems, the oxygen ions move through vacancies. And so what we did is we considered a big supercell, a big piece of these systems. We removed one oxygen atom in the simulation, and then we let the system live. We looked at the dynamics, and that was to understand how the oxygen atoms move and how easy it is for the vacancy to actually go from one side to another in the lattice and diffuse in the lattice. And so to do that, we had two different methodologies at our hand. The first one was ab initio molecular dynamics. So this is where the forces on the atoms are computed using density functional theory. So that's quite long and expensive. And so at that time, there was also an alternative methodology that was emerging, and that was using machine learned interatomic potentials to compute the forces that the atoms felt. uh, that was supposed to be much faster, but at the time it was still new, so it needed to be tested. And so here we were using ChargeNet. Now there are many, many more different kinds of models. But so in ChargeNet and in these other machine learning interacting potentials, the forces are predicted using a machine learning model, and this model has been trained on DFT data. And so it's supposed to achieve close to DFT level accuracy, but at a fraction of the cost. So that's why it's very, very competitive and very attractive as a methodology. And so these are the results using ChargeNet, so the machine learned interatomic potentials. On the left, it's cobalt oxide. On the right, it's nickel oxide. We have to look at the yellow dots here for oxygen, and this shows the mean square displacement. And how to interpret this is basically if this stays around zero, then the oxygen atoms are not moving, basically. And the higher it goes, the more the oxygen atom move in the crystal. So you see that on the left, there's a bit of movement, but not that much. On the right, there's nothing at all. And then if we crank up the simulation temperature, so the simulation temperature is high, but it's just to trigger more events. It's to see more of what's happening in a shorter simulation time. It's not the actual temperature of the system that they're doing in the lab. It's just for the simulation. When you increase the simulation temperature, then you see that in cobalt oxide, the oxygen atoms indeed start to move, while in nickel oxide, they are not moving at all. And so we do see that the oxygen ion migration is easier in cobalt oxide than in nickel oxide. This is what was observed experimentally. So that's good. But this is still a qualitative analysis. It's not fully quantitative because it depends on the quality of the machine learning potential. And ChargeNet was and is still a good tool, but it's not leading to fully quantitative results in the end. And so we wanted to have something quantitative, and what we did is we computed the energy path of a vacancy going from one lattice site to the other, and we did that using density functional theory that was with quantum espresso. So these are the results. Again, on the left, cobalt oxide, on the right, nickel oxide. And so here, the x-axis is the configuration coordinate. -1 means that it's a vacancy at one specific lattice site. +1 is the vacancy at the adjacent lattice site, so just one lattice site next to it. And so you see that to go from one to the other, the vacancy has to go through a higher energy state. And so it has to go through an energy barrier. That's what we call the activation energy in an Arrhenius flow like this. And so the results are there. You see that the activation energy in cobalt oxide is 1.2 eV, and in nickel oxide is 2.2 eV. So it's almost twice as much, but then it follows an exponential law. So it's even more than that in the end for the dynamics. So this really helps understand why in cobalt oxide they were observing that it's easier to remove and to put the oxygen atoms into the crystal. So this again has been published in this paper that is open access, like the one that I've shown before, and that you can go check out for all the details. We can also discuss the details in the question time. So this takes me to my take-home message. So first, active learning has indeed proven useful and successful to optimize an experimental process. So it's not only materials design, but also how to deposit and actually make these materials. So in this case, it was the nickel tungsten films that are used for catalysis. We also use DFT and machine learning interatomic potentials to better understand properties that are quite complicated. The diffusion of oxygen of atoms of ion in a system is not easy to do, but we can do that using DFT or machine learning interatomic potentials, and we can even do that in magnetic materials that are more difficult to simulate than, let's say, silicon, for instance. So these tools are indeed very useful to accelerate materials design and also the efficient development of processes. And these are the tools that we use in NICKEFFECT. We are also working on other projects, but that might be the subject of a next communication. So thank you for your attention. I will welcome questions, I think, during the question time or now, I'm not sure.
Thank you. Thank you very much, Guillaume. A very nice and interesting presentation. We will indeed address the questions at the end of the presentation, so we know that we have
Okay.
time all settled. So now we will pass on to FreeMe presentation. And today with us we have Costas and Albert, both from Exelis and Edenair companies. I don't know which one will start, but I assume it's Costas from Exelis. The floor is yours.
Hello, just okay. Hello from my side. I'm Kostas Pyrgakis from Exelis and also Albert Sabatel from Edenair. We are here also to spend a few slides to present the FreeMe project, another project funded under the same topic. And this project is oriented into the development of a safe and sustainable by design platinum plastics technology. So in this presentation, I'm going to give you a brief introduction of the one of the main FreeMe technologies, and then we will pass with the development of the property models for the materials, for the plastics, which are etched and plated by this new technology. And also we will jump to the second round of modeling, including the multi-scale modeling for the used materials. So plating and plastic industry, we can see many examples in our everyday life, like components in home appliances or cars, or other applications where actually plastics, due to being lightweight and low cost, they are preferred to coated by metals in order to, of course, from one side for protection purposes and of course for aesthetics. And in fact, the conventional approach running already includes these three main steps, where actually the plastic here on the left actually is etched by hexavalent chromium, and then the etched surface is activated and reduced by using a palladium tin mixture, and then the surface, the prepared surface of the plastic is then plated at the final stage. So definitely we can identify that the use of hexavalent chromium, which is it is a carcinogenic and highly toxic materials from one side, while at the same time palladium is a critical raw material, raise significant needs regarding the development of an updated, safe and sustainable by design plating and plastic process using non-toxic, environmental friendly, REACH compliant materials, and of course abundant materials. So in this concept, in this scope, here comes FreeMe, where actually the etching process, the hexavalent chromium has been proposed to be replaced by Piranha solution, which is a mixture of hydrogen peroxide with sulfuric acid, while the activation and reduction stage can be separated into two consecutive stages, where the first activation happens with the use of nickel salts, while then the nickel ions, which have been chemically adsorbed on the etched surface, are reduced by using sodium borohydride. And finally, we have, of course, the plating stage, which more or less remains the same as the initial, the conventional approach. So I'm going to give you a very brief intro about each of these four steps proposed by FreeMe. So let's go to the first one, which is the etching by using Piranha, where actually sulfuric acid works as a carrier, taking the hydroxyl groups from the hydrogen peroxide, and then it breaks, it cleaves the double bonds of the polymers, of the plastic polymers. And here in the case of FreeMe, we have ABS. And by this means hydrophilic groups, including carboxylic groups and hydroxyl groups, are formed on the surface. And as a result, hydrophilicity is a metric of the performance of the etching process. And actually one property which can be used in this case is contact angle. And actually contact angle is the first property that will be modeled in this work. Secondly, we have the activation, where actually here you can see the hydroxyl groups from the previous step on the surface. And by this mean, by using a nickel salt bath, we are chemically absorb the nickel ions on the surface, while next we are using the sodium borohydride mixture in order to reduce for the reduction of the nickel to metallic state. And actually we are developing the actual nucleation sites where the metal, the metallization procedure will initiate on the surface. And here we come to the metal plating, where here on the left, here you can see the blue substrate, and here on red dots, you can see the actual activated sites, the nickel sites prepared by the previous stage. And here comes an electroless plating process, where starting from the activated sites, gradually a film, a metal film is developed on the surface of the plastic. While later on you can further implement one, two, or more additional layers of metals. Like here in the case of FreeMe, we were implementing a second layer with by means of a nickel electroplating process. And here it comes, the two property models. The one main property model refers to the contact angle, which is actually a metric of how well a plastic surface has been etched. And secondly, we have also developed a property model to estimate the adhesion of the metal coating on the plastic substrate. So here it comes some models. So here you can see a graph where we have the contact angle versus the time of the etching process, right? And here you can see the different lines for the different Piranha solutions. And definitely we have identified that here there is a pattern. So here we have an incentive to correlate contact angle with the Piranha concentration and the time. And by being inspired by a Debre equation model and by considering fundamental boundary conditions, like at the 0 time, you have the initial contact angle of the non-edge substrate, while at the same time contact angle is reducing versus time. Then we have developed a first model, where here in the model you can see the estimation of the contact angle, while different parts of the model, parameters, and also equations inside the model, they are material specific. And here you can see also the effect of the time. And here you can see that we have another parameter in the model, what is also affected by the concentration of the hydrogen peroxide. So going further and in order to introduce the hydrogen peroxide effect, here you can also see that we can identify that there is also an optimal concentration where the contact angle could be minimum for different cases. And we have been also again inspired by a deeper equation, and we have accordingly developed a model for the estimation of the parameter of the model affected by the hydrogen peroxide concentration. And here comes the whole model, where the contact angle is estimated versus time and versus hydrogen peroxide concentration, where parameters are also included, which are material specific. And by this means, we have also fitted, of course, all these models to different kind of experimental data coming from Creative Nano, which is also the experimental group, the experimental team who is developing the technology, and we have reached quite satisfactory R-square metrics. So quite briefly, there is also another model made for the activation stage, where actually here we have made the correlation between the contact angle and the hydroxyl group's concentration on the surface, as well as the effect of the hydroxyl group's concentration on the surface versus the different activation, nickel activation concentrations. While for the case of the reduction stage, we have also developed a kinetic model, and by combining all these models, we could actually estimate the concentration of the nucleation sites on the surface. And by knowing this, you can go to the plating stage, and by this means you can make a correlation to estimate and to predict the adhesion for different kind of conditions. So here you can see actually in red dots the concentration of the nucleation sites made by the previous stages, and we have also identified that there is a correlation of this concentration based on which the electrolysis plating is spread across the whole surface and making this layer. While later on, since we also have an adhesion also between the two layers, we could also have also introduced into the model a second level of relationship related with the electroplating process, and actually the development of the layer over the electroless layer. And by this means, we have developed an approximation to predict a function in order to predict the adhesion based on the different conditions of the operation, having also higher than 0.85 R-square fitting performance. And last but not least, actually, just as a brief intro, it's not the purpose also of this webinar, but all these models actually could be integrated into a decision support tool later on. Maybe this could be another presentation another time, where you can include the property models along with unit operation models and develop a decision support tool based on which the user could include the items characteristics and the adhesion specifications, and the decision support tool could make best propositions regarding the design of the FreeMe technology and its processing stages. And by this, the first part of FreeMe, actually, my part from Excel's side is done. And now let me also pass the floor to Albert from IDENER.
Oh, thank you so much, Costas. I think it was an extremely interesting presentation. And okay, I will share my screen. I guess that everyone can see it? Oh, yes. One moment. Okay, can everyone see my screen? Yes. Nice. Okay. So, well, thank you. Okay. Okay, I will be very brief because I think that more or less, given the audience, I think that everybody knows what multi-scale modeling is. And actually, Guillaume has already presented some the most crucial points of this, let's say, formalism or techniques that we are also using on FreeMe. So basically, the idea is to couple different um, size and time length models, starting from the lowest one that would correspond to the atomistic scale models that corresponds to DFT simulations, and then trying to couple it to why this it happened? Okay. Sorry. And then try to couple it um, in order to increase the time and the mass and length scale of the models until reach eventually, if it's necessary, the high level macro scale models that would correspond, for instance, for CFD simulations. In this case, I'm using this uh, this illustration from typical heterogeneous catalysis process that can be used for any kinds of chemical processes. So just returning from the general to the more specific part for FreeMe, the idea is, wait, let me just put this here. The idea is to create these multi-scale models to model the process that Costas has already explained. So we will be focused on two main objectives. So to generate models to sprayable composites to explain the sprayable composites on resins. So the idea is to use ab initio quantum mechanics and molecular dynamics in order to get insights on this kind of process. Then we will couple what we get from the simulation to Monte Carlo simulations, and then we will use this to build some coarse-grained and continuous models. Then the other idea is to try to understand the plastic surface etching processes, from which we will use MD, MC, and at some point we will also use computational fluid dynamics. I have to say that at this point of the project, we have not started yet with the CFD simulation, so the computational fluid dynamics, something that we will do more in the future. So starting by the etching process here, we have modeled this reaction process in which I'm presenting only the polyacetronitrile reaction with piranha solution, in which basically what we are simulating, it's the transformation from this acetonitrile group to this amida group. Okay, so basically what we have found is that it's an exothermic process. So basically it's something that it's possible to happen with maybe a little bit of energy, because we found that we have a transition, a rate determining step here that would correspond to the formation of this amida group. Okay, here the graphic is set in Hartrees. So actually that means that the barrier, the activation energy, sorry, for this process would correspond to approximately 0.8 electron volts. So that means that can happen, but maybe we will require some kind of temperature in order to make this process. Okay, and then after this, we move from the DFT simulations to the MD simulations and kinetic Monte Carlo, from which we were from the MD simulations we were able to estimate the ability of the piranha solution to interact with the ABS, and then trying to see if it was able to penetrate the surface of the polymer and see how it could affect and see how it could affect the structural parameters, let's say, of the of the polymer in face of this solution. So then we wrap up all this information, both DFT and MD simulation results, into kinetic Monte Carlo simulations, as you can see here in my right part of the presentation. Okay. We use the kinetic Monte Carlo simulation because instead of, for instance, a mean field, because we were interested on also saying, also looking at the different lateral interactions, and also to take into account the anisotropy of this process. So it's not the same how the piranha solution might attack each one of the monomers depending on the initial configuration of our lattice, and for sure on the presence of the different neighbors. And as you can see, what we could basically see is that after some steps, the solution actually converts to the formation of the oxidized polybutadiene, and also the oxidized acylonic field. Okay, which actually is exactly what we would expect from experimental point of view. Okay. Then we also were, as I said before, we were also generating coarse grain simulations. In this case, we are not working with the etching. We are working directly on the deposition, okay, of nickel on nickel on the ABS substrate. Okay, so to do so, we generated this workflow that actually is fully automated, written in Python and Bash, and using Gromax as the coarse grain simulation software. So first of all, we generated the input preparation by just defining each one of the bits as ABS and connecting them as you see in the figure. Then we run an energy minimization and run an MBT and then an MPT stabilization for finally get a proton simulation. Okay, the final effect, or let's say the final state of the simulation would be very similar to what you see here in my right place, in my right corner of the presentation. Okay. And then from that, we can extract the following information. First of all, which actually it was at least surprising for me, is that the nickel mainly prefers to sit in near B and S monomers rather than acetonitrile. Maybe this is due because we were using the Martini force field to define each one of the monomers and also nickel, and probably the Martini use for A, and also for A uses a kind of, let's say, polar kind of interaction, while for B and S, for B would be something that we can define more like hydrophobic, and S will be more related for aromatic to more aromatic and maybe not that reactive uh, force field. So basically, what we see, and in the case of nickel, probably they are kind of using also some kind of polar interaction. What could explain, I think, we think, this kind of distribution, which actually it's totally independent from the temperature and pressure. Then what we can do also, it's count the total number of nickel contacts with the A, B, and S bits in order to get some kind of some kind of estimation of the coverage of nickel on the surface of the ABS bunch of the ABS chunk that we have built as a function of temperature and pressure. We have took this kind of temperature and pressure ranges because first we wanted to investigate what happens below the temperature or the glass transition temperature of the monomer and above that temperature, that value. And what we can see basically is that we can see that the coverage of nickel would decrease with temperature, while we are not very sure to find any kind of let's say of a relationship or trend with pressure, which actually I think that it's something that also makes sense. So, and finally, from these results, the other thing that we can do is to extract some kind of apparent activation energy. To do so, we used an extremely, I think, common and easy Arrhenius relationship in which we have calculated the velocity or the rate of adsorption of nickel on the ABS, and then we can represent this 1 over T this our 1 over T plot, and then the slope would correspond to this apparent activation energy that actually Guillaume was mentioning before, but in the case of the atoms diffusion, in this case would be an adsorption. And with that, we can develop a surrogate model that will come directly from adapting the typical Hertz-Knudsen equation for adsorption, assuming that for gases on surfaces, assuming that nickel would have a kind of similar behavior. And actually, it works pretty well, I have to say. And this can be used as a surrogate model that we can then plug on higher scale models, such as CFD simulations, or yeah, there are basically this or in order to have a more, let's say, one-to-one comparison with the real experiments. And then just to recapitulate very shortly, so we have used different scale methods for ABS etching process and nickel deposition on ABS. So that second let's say that's first objective, that deposition experiments that we wanted to investigate. Then we are able to do energy predictions for etching and also for nickel deposition. We also can have some kind of penetration depth predictions, etching patterns, also with nickel deposition patterns, nickel coverage estimations. And finally, we have been also able to generate a nickel deposition surrogate function or model that we can just unplug or plug into the higher level models, such as CFD simulations. And that's all. Thank you so much for your attention.
Thank you very much, Albert and Costas, for your presentations. Very interesting, very insightful. We will jump now to the Q&A part of this webinar. We already have 3 questions here in the Q&A box. Just a quick reminder before starting the Q&A session. I will ask all participants, since the chat box feature is disabled, please use the Q&A feature that you have in the drop-down menu that we have on the webinar here within Zoom. So the first question that we have here is towards Guillaume from Mechanics. And the question goes, I find the use of machine learning for optimizing electrodeposition processes very powerful. Do you think this approach can be applied universally to any electrolyte bath and material system? And how easily could such a method be integrated into the everyday of an experimentalist?
So yeah, because I mean, it could be used on any data set, basically. It's machine learning. It's a methodology that you can apply to any data set that you have. You have inputs and outputs. So as long as you are able to gather at least, let's say, 10 experimental results for which you have the inputs that you know, like the temperature, the current density, and so on, and the output, in this case, it was the Tafel slope, the over potential, and then the score. You can identify any output depending on the experiment that you are doing. You can also use different inputs, and the methodology is very general. You can use that for any kind of systems, any kind of property. Of course, depending on the complexity of the system, of the process, you may need more data. That is case by case dependent. So you have tests to do, but you can assess the quality of the model as well. So yeah, indeed, it can be used. It's very general. It can be used to any data set and any experiment. The fact that it could be integrated into the everyday use of an experimentalist, this is already something that is deployed in some companies, in some labs. There are these automatic data collection tools that you can have, that you can deploy in your lab. And so the data will be collected automatically from the machine to a database, and then the database can be connected and can be developed so that machine learning models are automatically trained on this data and can provide the experimentalist with some help. So that is something that is already done in some places, in some labs. It's not yet used universally, but it can be done. So I would say that if the person asking this question wants more detail, they can send me an email, and then we can go into more details, or I can give some links to useful packages that can be used to deploy that, and examples of that. It's something that we do at Magenics as well.
Perfect. Thank you, Guillaume, for answering this. The following question will go to the FreeMe representatives. And it goes, first of all, I would like to highlight the great collaboration between the modeling and simulation teams. You mentioned that some parameters in the model are material specific. Was the model designed particularly for ABS plastic? If another plastic were used, to what extent could the model still predict the angle properties?
Yeah, that's a very good question. In fact, actually, the model development concept seems to have a quite, let's say, high level of generality. And this is, I can say this because we have tested this model for four different types of ABS, including PC-ABS. But to be honest, not this model as it is could be used definitely for all types of polymers. And why this? Because different groups of polymers we have seen in literature, they feature similar or quite different, let's say, behavior in terms of contact angle. So we could say by verifying this model with four different similar polymers, we could say that it could be quite well to fit the contact angle for polymers that they are using in high level, let's say, similar monomers. Still, when you want to extrapolate and go to other types of materials, due to the generality of the different terms, because the model actually includes a big, a wide range, let's say, of terms which can simulate different kind of behaviors, different kind of lines, you could minor or major and sometimes modify the existing model to capture, let's say, the contact angle for different polymers.
Thank you, Costas. We have an extension of this question, and
Okay.
it is also for the electroless electroplating step. Did you assume a flat substrate in your simulations, and can the model be used to estimate the thickness of the deposited layer?
Okay, yeah. So as far as concerned the adhesion specification, which was one of the property which is modeled here, yes, there is one part that has to do with the material that is deposited on the substrate. So yes, thickness in terms of mass is also considered for the estimation of the adhesion. To be honest, not that large effect compared to the concentration of the nucleation sites that have been developed from the activation stage. But still, also thickness is also estimated into the whole model. As I said, all these property models are also part of the DST, Decision Support Tool. Actually, the thickness is also another metric that is computationally measured, because the user could also set a specification goal for the thickness, and accordingly the model tries to optimize the process to reach all specifications at the same time.
Okay, thank you very much, Costas. The next question we have is for Albert. And it is for you to specify, maybe it was something that was missed by the person who asked this question, but maybe could you specify on slide 19, what is the resolution of the surface distribution maps?
Yeah, actually, it's I don't know if is that what you are referring to, but this map is made in angstroms. It's this what are you asking? It's what are you demanding? Nice. Yeah, in angstroms. Thank you.
Okay, I think we don't have any more questions here in the Q&A feature of the webinar. With that being said, I would like to thank the three of you for presenting today and for giving such insightful presentations. For sure, they will be memorized and will be shared with every participant here in the NICKEFFECT and FreeMe webinar. I would like to remind everyone that this session was recorded, and we will provide in the near future the recording in NICKEFFECT YouTube channel. FreeMe will also share with these contacts, and that's it. Thank you all very, very much for joining us today.
Thank you.
Either you.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.